Is it visible to everybody?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes.
Okay. Yesterday we have started with the analysis of doubly reinforced beams. We have seen how doubly reinforced sections are defined and in which situations or conditions we need to design the beam as a doubly reinforced section. We also discussed about the assumptions, additional assumptions made for the analysis of doubly reinforced section, the basic concepts involved in the doubly reinforced section, and also seen how to derive the various parameters, that is how to find out the depth of location in case of doubly reinforced section, how to find out the moment of resistance, and also how to find out the area of the steel provided in tension zone as well as area of steel provided in compression zone. So today we will see now how to actually calculate the moment of resistance, XU value, and the other parameters. So I have just included all these diagrams to recall the concepts which you have learned yesterday. This is the beam, actual beam section of doubly reinforced section, which we assume as made of two sections, section 1 and section 2. Section 1 is considered as a singly reinforced section, which have no reinforcement in compression zone, and section 2 is the imaginary section in which there is only the compression zone in the there is only the compressive steel in the compression zone along with the sum of the steel in the tension zone. Okay, then these are the stress distribution diagrams. Overall, this is the overall stress distribution diagram for doubly reinforced section. And these are the stress distribution diagrams corresponding to section 1 and section 2. How we get the total force of compression CU and PU, yesterday only we have learned. Now, we also learned about all these derivations, XU formula, how we arrive to this formula, then MUR formula, AST, total area of the steel in tension zone, AST1, AST2, how we are getting, and finally the total area of the steel in compression zones. And just to recall the yesterday's concept, I have included these formulas. Now, we have started with how to find out the stress in compression steel. I will quickly go back to the earlier slide and just want to focus your attention on the XU expression. If you consider the XU expression, as we discussed yesterday, there are some constant terms, that is 0.87, 0.36, then some constant value for given section of a beam, that is the width of the beam, then the grade of the steel, grade of the concrete. Area of the steel and in tension and compression zone is also known to us if a section details are given to us. What is required to find out? The stress in compression steel, that is FSC. Okay, now today we will focus on how to find out the FSC. For that, as discussed yesterday only, that for a given doubly reinforced section beam, we have to make use of the strain diagram to find out the FSC, that is the stress in compression steel, because the stress in compression steel depends upon the stress at the level of compression steel. That is, the steel in compression zone is present at this level. At this level, what is the strain? That we have to find out, and based on the strain value, we have to find out the FSC value. So to find out FSC, we have made use of this strain diagram in which there are two similar triangles. This is the bigger triangle and this is the smaller triangle. Both these triangles are similar. So by making use of or the concept of similarity of the triangles, we have written these equations. Okay, so we have calculated or we have expressed the strain in compression steel epsilon SC in terms of DC and XU. So we obtain this formula 0.0035 into bracket 1 minus DC upon XU. And then we have made use of the Hooke's law, which is applicable especially for mild steel, because in case of mild steel, the stress-strain relationship is linear up to the yield point, and hence the strain or beyond this yield point, when the strain increases, the stress remains constant. So we consider only the elastic limit or the relationship of stress and strain within elastic limit for mild steel. Okay, hence by considering Hooke's law, we can easily find out the relation between stress and strain, whether it is in compression zone or tension zone. We can use the same concept. So right now we are interested to find out the stress in compression zone. So FSC we are representing in terms of strain in compression zone, compression steel, that is epsilon SC into modulus of elasticity E. And there is a limitation to the FSC value, that it should not be greater than FYD. That is the maximum yield stress, which is given as 0.87 FY. Okay. Now we have put the value of epsilon SC, whatever we have obtained here, in this equation, and after simplification we get the expression for FSC as 700 into bracket 1 minus dc upon xu, and this value is limited to maximum of 0.87 fy. Now this is a very straightforward method to find out the FSC for mild steel. The same case is not applicable for HYSD steel, because we already know that for HYSD steel, the stress strain relation is not completely linear. That is, up to certain point, it is linear, and beyond that, the curve turns out to be non-linear. Okay, so we have already discussed the stress strain relationship for HYSD bar in a very first week of SG1 lectures. So from that, if you are able to recall this stress strain curve, okay, the same curve is also available in IS 456 page number 70. Okay, I will come to this diagram in detail, or quickly I will show you the same diagram in code also. If you have a code copy right now with your hand, with you, page number 70, you can find out the stress strain curve for mild steel. This is for mild steel, and this is for HYSD bar. So same diagram I have taken in my presentation here. Now, if you observe this curve, this is the curve for HYSD bar, in which the curve is linear up to this point, where the pointer is there, and beyond that, this is the non-linear portion. So for this non-linear portion, obviously we cannot apply the Hooke's law, because Hooke's law is applicable only for the linear part of the curve. So up to this point, that is from 0 to up to this stress value, we can apply the concept of Hooke's law for HYSD bar, whereas for this curve portion, we cannot use that particular concept, and we need to find out the strain by making use of this curve itself. Okay, so same thing is written over here. The stress strain relationship is linear up to the design stress of 0.88 Fy upon 1.15. So I will go back to this curve, and if you observe the value over here, this value is 0.88 Fy. Now there are two curves you can observe in this graph. First one is the curve related to characteristic stress values, which is presented by Fy, and second curve is the curve corresponding to design stress. So design stress values we obtain by applying a partial safety factor. For steel, it is 1.15. So this curve corresponds to design stress factor, in which the Fy value, whatever is the Fy value, it should be divided by 1.15. That's why the curve is represented like this, Fy upon 1.15. Now all these values are shown for the characteristic stress curve. Okay, here we have to apply a partial safety factor, and then the corresponding value we have to consider in the calculation. So if you consider a point over here in this curve, up to the value of 0.8 Fy, the curve is linear, and beyond this, the curve is non-linear. Is it clear, students? Are you there in the class?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, okay. So beyond this point, if I want to find out the strain, it is not possible to make use of Hooke's law here, because the relation between stress and strain is not linear. For that, we have to make use of the concept of inelastic strain and elastic strain. Now, if we consider any stress along this linear part of the curve, the strain corresponding to this portion is called as elastic strain, and that elastic strain we can easily find out by applying Hooke's law, that is epsilon equal to F upon E, okay, by using this formula. But the same formula is not applicable in non-linear portion, and in non-linear portion the corresponding strain values are called as inelastic strain value. Okay, So inelastic strain values are calculated by trial and error method. Okay, and after calculation of the strain values, we can again find out the neutral axis depth of the neutral axis by trial and error method. So I will just read out whatever is written here. The stress strain relationship is linear up to the design stress of 0.8 Fy upon 1.15 and non-linear till it reaches a value of Fy upon 1.15 at a corresponding strain of Fy upon 1.15 Es plus 0.002. Now, if you consider this strain value, there are two parts in this strain. The first one is called as the elastic strain and second is called as non-elastic strain. So again, I will move to the curve here. So 0.8 Fy upon 1.5 up to this point, that is, if I will go to this point, this curve, this is the point where I'm getting the 0.8 Fy upon 1.15 value. Okay, so that value, the curve is linear, and beyond that, the curve is non-linear up to Fy upon 1.15. So this value is actually Fy upon 1.15. That is, we are getting as 0.87 Fy here. Okay, so all these portion, for all these portion, whatever the strain value we are getting from this curve, all these strain values are called as inelastic strain value. Okay, if you observe at this particular point corresponding to this, the strain value is 0.002. So the strain value in elastic portion plus 0.002 is the maximum strain corresponding to this highest strength value, which is given here, this value. And this is the maximum strain developed in a steel at the time of failure as per the assumption of limit state of collapse. Okay, now let us see how to find out these elastic strain and inelastic strain. So total strain will be strain value for the steel will be elastic plus inelastic value. Okay, so we will quickly prepare a table here. Everybody has to make the same table in your notebook, and we are going to do the calculation here. Now, this table gives us, or we are actually interested to find out the total strain value for Fe415 steel. Okay, so strain values we have to calculate by making use of this curve. In this curve, you can find out different stress values are already given here, and corresponding to these stress values, the corresponding inelastic strain values are also given. For example, if I'm considering 0.80 Fy value, the corresponding strain value is 0 here. If I'm considering 0.85 Fy, the corresponding strain value over here is 0.0001, 0.0001. Okay, 0.90 Fy stress value, the corresponding strain value is 0.003, 0.0003. Okay, similarly, for 0.95, the value is 0.0007. Are you getting these points, students?
Yes, ma'am.
Okay. So the same values I have written here in the table. Design stress 0.80, 0.85, 0.90, 0.95, 0.975 and 0.87 Fy. Okay. So if I will go back, you have to constantly refer this curve now from IS 456. Everybody has to open this curve right now with you. Open the this particular graph from IS 456. You have to constantly look into the curve, look into the graph. Then and then only you will understand how we are doing the calculations. Okay. So this is the value. One thing I want to make a correction over here again. So this is 0.87 Fy is the final value. So I have to write down this as 1 Fy divided by 1.15. It is equal to 0.87 Fy. Okay, this correction I will quickly make. Okay, so are you preparing this table in your notebook? Students?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Have you prepared it or you are writing right now?
Writing,
I'm
ma'am.
writing.
Okay,
Writing, ma'am.
okay. So all the design stress values I have written over here. In the second column, the value of this expression is written over here. Then the corresponding inelastic strain values are also written based on the values given in the curve of stress strain. Then elastic strain values we have to calculate by making use of this relation. This is simply a relation as per the Hooke's law. And finally, we have to find out the total strain as addition of these two strain values. We will prepare this table first and then we'll go to the numerical examples. Once you finish of making this table, please tell me. Then we will start the calculations further.
I mean, the last column, what was that? 0.8, only 0.87 FY is there.
It is the value of Fy upon 1.15. Actually, if you see this value, it is 0.975. This is 1 Fy divided by 1.15. So it is coming as 0.87 Fy. Is it over?
Yes, ma'am.
Yes, ma'am.
Okay. Let us see now the first row calculation. I have already given the values over here, but how we have obtained these values, I will quickly explain you. First is 0.8 Fy upon 1.15. I want this value, which is coming as 288.70. Put the value of Fy as 415 here and do the calculation. You will get this value. Okay. So same is done here in the next slide. So design stress value is 0.8 Fy divided by 1.15. So I'm getting it as 288.70. Now corresponding to this strain value, stress value, if I will look into this curve, 0.8 Fy, this value, the corresponding strain value is 0 here. So the value is written here as 0. This is the inelastic strain. Okay. Now we have to find out the elastic strain value, which we can find out by making use of this relation. What is F value now? F is 288.70 divided by E is 2 into 10 raised to 5. So F upon E, I'm getting 0.00144. So the same value is written here. And the total strain we can calculate as addition of these two strains, inelastic strain plus elastic strain. So here in this case, the inelastic strain value is 0, elastic strain is 0.0014. So the total strain will come out to be 0.0014. Is it clear? Calculations?
Yes, ma'am.
Yes, ma'am.
So as we have did in the last previous lecture, we have completed this table. In the same fashion, we are going to complete the table right now. So quickly, everybody has to do the calculation for second row and tell me the values. Meanwhile, I will write down here the total strain value, which is 0.0014 as per the calculation.
Ma'am, design stress value is 306.73.
306.73. Correct.
Yes.
73 or 70? What is the value?
Actually, 74. 739 was that. 74.
Okay. So it is 74. Then the inelastic strain value is 0.0001 as per the curve. Find out the elastic strain F upon E. And tell me the 5-digit number after decimal.
0.00153.
153. Correct. Tell me the total strain value. It will be the addition of these two values. So 0.00153 plus 0.001.
0.0016.
163. Okay. Okay. Next.
324.78.
320.
4.78.
0.78. Okay. Correct. Tell me the elastic strain value.
0.00162.
Correct. 0.00162. Total strain.
0.00192.
Correct. Next.
342.83.
342.83.
340.
2.83.
Okay. Elastic strain.
0.
Correct.
0.00171.
Total strain.
0.00241.
Okay. Correct. Next.
351.85.
351.85. Okay. Elastic strain.
0.00175.
75. Okay. Total strain.
0.00275.
Okay. The last one.
360.86.
361.05.
360.86.
360.86.
Okay.
0.0018.
180.
1.
Okay.
181.
All right. Total strain.
0.00380.
Okay. Correct. All these values are absolutely correct. Now, similarly, you have to prepare the table for FE 500 also. See why we are preparing this table in the examination when we solve the problems based on design of or analysis of doubly reinforced section. And if FE 415 steel is provided, you need to use the values from this table. I mean to say, when you will solve the problems, you definitely come to know that why we need to prepare the table. At that time, you need to prepare the table in the examination also. If Fe415 steel is given for doubly reinforced section, you have to prepare this table first, and then during the calculation, you need to find out the value by interpolating these values, because the stress value will not be exactly the same value which we have written here. The actual stress in the steel in compression zone may vary between any this value. It will be 0.87 FY maximum or minimum any value. So for any corresponding value, what is the strain value that you need to find out by interpolating only. Okay, and for that you have to prepare this table in the examination. It is not possible to mug up all these values. Okay, and I think there is no need to mug up the values also, because you have already this curve in IS 456. So you have already the design stress values and inelastic strain values. Only the thing, the calculation part is you have to find out these values and these values. Elastic strain and total strain. So you have to prepare the table. So you should be able to prepare the table in the examination also while solving the problem. So my suggestion is that you have to prepare the table for FE 500 also. So will you do it as a homework or shall we do it right now only? Hello?
Ma'am, I had a doubt.
Huh?
Do only find out one value.
Your voice is breaking.
Ma'am, now am I audible?
Yes.
Hello? Ma'am, if there is given that design stress,
Uh,
we can calculate that value only, no? Why there is a need
wait.
to calculate all?
Your voice is still breaking. I'm not getting the clear question.
Hello? Hello,
Huh?
ma'am.
Huh?
Ma'am, if the design stress is given in between 80 to 85, sorry, 0.80 to 0.85, FY
Huh?
upon 1.15, then instead
Huh?
of calculating the whole table, cannot we just find the only one value, only one single row?
Yes. No problem in that case. In that case, it is no problem. But suppose the stress value comes out to be between 95 and 0.97, 0.95 and 0.975. Only these two values you can calculate and find out the interpolation. No issues. But you should know basically how to calculate the values.
But why there is a need to interpolate? We can just directly use that value, which one we want.
Suppose the stress is coming as say 0.93 Fy upon 1.15.
Yes.
0.93 Fy upon 1.15. Okay, how will you find out the total strain for this value?
Okay, from graph we don't have it. So.
From graph, we don't have the values of inelastic strain. Okay, and the graph is also not so clear. If I will refer your code here, it is not so clear that we can simply just find out what is the corresponding value for 0.93. Okay, this is my value, put the point here and draw a line parallel to here and find out what is the value. This is not possible because the grid is not here. We don't know what is the scale of the graph. Okay, so from the graph only these values are available. In that case, only one way is there, that we have to interpolate the value.
Okay, ma'am.
And that too we are interpolating assuming that there is a linear interpolation. To be very frank, these are the values on the non-linear part and we are finding it interpolating. The interpolation is normally done for linear values, right?
Yes, ma'am.
So still we are getting the approximate value even though we are doing the interpolation, but these values directly we cannot use if the stress value is something different than these given values. Is it clear?
Yes, ma'am.
Okay. So I had asked one question whether we are preparing the table for FE 500 right now immediately or you will do it as a homework.
Ma'am, now.
Okay. Everybody agree with this? Students?
Yes, ma'am.
Okay. So I will simply copy the same table in the next slide and I will make the change over here that this is for 500. Now we will calculate. So these values will also change because Fy value is getting changed. So we have to calculate this also. We have to calculate these values also. So tell me quickly the first value.
347.83.
347.83. Okay.
Zero, 0.00174.
Correct. Total strain will remain the same because the first value inelastic strain is 0. So this is the same value. Okay. Let us consider the next value.
369.57.
369.57. Okay.
0.00184.
184. Okay. Total strain
0.00194.
194. Okay. Next.
391.30.
Okay. Elastic strain
0.00195.
195. Yes. Total value
0.00225.
okay. Next
413.04.
413.04. Okay.
0.0021.
Okay. Tell me the next digit also. It is 210.
Ma'am, it is actually 0.00206. So I round up and 21.
No. Let us consider the full one.
0.00276.
0.00276.
ठीक है. Next.
423.91.
Okay.
0.00211.
Okay.
Total 0.00311.
Okay. Last one.
434.78.
434.78.
Okay.
0.00217. And
Correct.
0.00417.
Perfect. Okay. So we have prepared the table and you have got the fair idea how to find out the total strain in case of HYST bars. Now let us move to the next point, that is how we are doing the analysis of the problems. Now obviously the method of calculating the FSC value, that is the stress in compression steel, that method is different for these two grades of steel. The calculation or the analysis or the way of analysis of the problem is also different. Okay, so for mild steel we have to follow certain steps for finding the XU value or MUR value. Similarly, for finding the moment of resistance value or even the depth of neutral axis for HOSD bar, the steps are different because we are calculating the epsilon value, epsilon SC and FSC value in a different way. Okay, so we will see today only for mild steel and we will solve some numerical examples based on that, and how to analyze the problems based on HYSD steel bar, that we will see in the next lecture. So just write down these steps in your notebook, or I will simply explain one by one. Anyways, I'm going to share these PPTs on BOLP, so you can get the steps from there also. Right now, you just understand these steps. The first step is that we have to assume FSC value. Now, why to assume? Let me explain. If you consider the FSC expression, see, this is the expression for FSC, that is 700 into bracket 1 minus DC upon XU. This expression consists of XU term. Initially, we don't know what is the depth of neutral axis, and that is the first step in our problem solution, that we have to find out XU. So if you consider the XU formula, in XU formula, there is one term called as FSC. Here, I have actually submitted or substituted FSC value by this equation here. But if I will go back here in these equations, whatever we have written earlier, see here, in this equation, the term FSC is present for XU. And in the equation of FSC itself, again, the term of XU is present. So any one value we need to assume initially and then start the solution of the problem. Okay, so initially XU value we cannot assume because it will be anything value. XU will be anything, okay, anything within the depth of the section. FSC value, we know it has a certain limitation, that is FSC value cannot be greater than 0.87 FY. So it is easy to assume initially FSC value. So the first step is that we have to assume FSC as 0.87 FY. We have the FSC value, we can find out or we can calculate XU. So simply in the expression of XU, we will put FSC value as 0.87 FY and we will calculate the XU value. Now we have to compare the XU with XU max. It is the same step which we have done in case of analysis of singly reinforced section also. So by this step, we can find out actually the type of the section. If your XU is coming less than XU max, it means the given section is under reinforced. If XU is coming greater than XU max, the section is over reinforced. So if XU is coming greater than XU max, we have to limit the value of XU to XU max value. So if it is coming greater than XU max, take XU equal to XU max for further calculation. Now we have calculated the XU value. We have to again calculate FSC by making use of this expression. Initially, we have assumed the value. Now we are calculating the actual value based on the XU. So let us calculate the FSC value by making use of this particular expression, 700 into bracket 1 minus DC upon XU. Now this expression will give some value of FSC. We have to compare that value with the 0.87 FY just to check whether our assumption, initial assumption, is correct or wrong. Okay. So after calculating FSC value, we have to verify it with 0.87 FY. If it is equal to or greater than 0.87 FY, our assumption is correct. See, when we discuss the FSC derivation of this formula, it is clearly mentioned that we have to limit this value to 0.87 FY. Similarly, or similar to XU value, suppose your XU value is greater than XU max, we have to simply consider XU equal to XU max. In the same fashion, if your FSC value is coming greater than 0.87 FY, we have to consider the value equal to 0.87 FY, and that value we have to use in the analysis. Okay, so this is the comparative stage in which we are checking whether our assumption is correct or not. Initially, we have assumed it is equal to 0.87 FY. Suppose if its value is coming greater than 0.87 FY, we have to limit it to 0.87 FY. So the assumption is correct. If the value is coming less than 0.87 FY, it means our initial assumption is wrong. In that case, we have to recalculate the XU by substituting FSC in terms of XU. So our XU expression will be like this. So there are two XU terms in this equation. So we have to simplify this equation. Obviously, we will get a quadratic equation. We have to solve that quadratic equation and we have to find out XU. Again, we have to compare this XU with XU max to get the type of section here. Once you get XU here, find out again FSC. Once we get the final value of XU and FSC, we can calculate MUR by making use of the equation. Okay, so if you initially observe these steps, it seems to be complicated because first calculate FSC, then calculate XU, again check FSC value, again find out XU, again find out FSC. This is a repetitive step. Okay, that's why at least for mild steel, by repeating 2 or 3 steps, we are getting a certain value of XU and FSC. In case of HYSD, that method becomes iterative. We have to iterate it for 2 times, 3 times, 4 times, once or till we get a constant value of FSC. Okay, so the process of finding MUR or even XU is little bit tedious when we use the HYSD steel for doubly reinforced section. Is it clear? These steps?
Ma'am, if
Yes,
the
ma'am.
ma'am,
Yes.
ma'am, if the FSC value is greater than or equal to 0.87 FY, then we don't recalculate the XU by substituting the formula again. The step 4, we don't do that, no?
Yes, yes. We don't need step number 4. If FSC is greater than 0.87 FY, it means our assumption, initial assumption is correct. And based on that assumption, we have already calculated XU. So there is no need to follow for step number 4 and 5. if FSC is coming greater than 0.87 FY. Okay, then we directly go to calculation of MUR, because we have already calculated XU and that XU value is correct, and that XU value we will put simply in MUR expression, FSC value we will put in MUR expression, and will directly calculate MUR. Okay, so if this condition is satisfied, that is FSC is coming greater than 0.87 FY, we will directly go to the last step, that is calculation of MUR. If not, then we have to repeat these things again. Is it clear?
Yes, ma'am.
Okay. Any other doubt to any other student regarding these calculations? If not, then we will solve one numerical example today. Shall I proceed to the example?
Yes, ma'am.
Yes, ma'am.
Okay. So note down this example in your notebook. Calculate the ultimate moment of resistance of RC beam of rectangular section 300 mm wide and 380 mm deep for the following cases. First case, AST is given, that is area of steel, 6 number of bars of 20 mm diameter, and area of the steel in compression zone is also given, 2 number of bars of 20 mm diameter. Second case, the area of steel in tension, 5 number of bars, 20 mm diameter. Area of steel in compression zone, 5 number of bar, 16 mm diameter. The grade of steel given is Fe250 and grade of concrete is M20. Effective cover is also given as 40 mm. And the depth of the section, whatever is given, that you have to consider as the effective depth. It is not the overall depth. Okay, it is effective depth. So quickly write down this problem statement, then we will solve the example. Guys, whatever what I have told you, 380 mm deep, it is the overall depth, because effective depth cover is given here now. So this is the effect, this is the overall depth. 380 mm is the overall depth. Is it over? Have you noted down the problem statement? Students?
No, ma'am. No, ma'am. We are still writing.
Yes. Hello? Is it over?
Yes, ma'am.
Yes,
Ma'am.
ma'am.
So let us solve the problem. Let us write down the given data. So tell me the given data.
300 mm wide and 380 mm deep.
So B is 300 mm. Total depth is given as 380 mm. Yes. Effective
cover,
depth is, sorry, effective cover is also given. So
yes,
DC value, what is the value?
40 mm.
40 mm. Yes. Then we have to solve for first case, right? So we are
Yes,
solving here the first case. So for first case, AST is given. What is the value?
6 bars of 20 mm diameter.
Okay, so I will directly calculate the area here. So it is pi by 4 d square into 6. What is the value?
One 1.88
Uh,
meters.
wait a minute.
And we have to calculate it in meters.
Wait a minute. Wait a minute. Let me check the problem statement which I have given. Okay, it is correct. Yes,
I mean mm or meter.
it is mm, na? AST.
Okay. 1884.95.
1884.95
4.95.
mm square. All right. Similarly, ASC value is also given. ASC.
Yes, ma'am.
So let us find out its area. Pi by 4. What is the diameter?
20 mm.
20 square. And number of bars?
2.
2.
Okay.
628.31.
628.31
31.
mm square. It is also mentioned that it is FE 250, right? So FY is 250 Newton per mm square, and M20 grade is given. So FCK is 20. Okay. So what is the first step now in the calculation?
Assume FSC.
Yes. Wait a minute. This is the last time. Let me clear the board first. Sorry guys, I forgot to clear the board before starting the lecture. Do you have a practical at 3:30 today?
Yes, ma'am. One
Yes,
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 ma'am.
ma'am.
A2. A2 batch it is oral.
A2 batch oral?
Yes, ma'am.
Which subject oral is that?
SWRE and QSCT.
Okay. Both?
Yes, ma'am.
Yes, ma'am.
A2 batch, okay, both the batches are having different. No, how many batches practicals are there? All three batches?
All batches,
Yes,
ma'am.
ma'am. Also.
A1 batch?
Transportation
Yes, ma'am.
engineering practical.
Okay, okay. And A2, A3 are having orals.
Yes, ma'am.
Oh God. Finally finished. So the first step we have to assume FSC equal to 0.87 FY. Tell me this value, what you are getting. Put FY equal to
217.5.
217.5 Newton per mm square. Okay. Now the next step, we have to find out XU, right? Because we have FSC value. Tell me the expression for XU. Hello?
0.87 FY
Hmm?
into brackets AST1 plus AS2
Let us consider total AST because we have the total value, right?
minus FSC into ASC
Okay,
divided by 0.36 FCK into B.
correct. So let us put the values. Here it is 0.87 FY into AST. FSC also 0.87 FY. Okay, so I can take 0.87 FY common and I can write down that 0.87 FY into bracket AST minus ASC divided by 0.36 FCKB. Are you getting this point? Or shall I write down as it is? Let us write down as it is. 0.87 FY. Okay, this value we have already calculated 0.87 FY. So I am putting it directly here. 217.5 into AST is 1884.95 minus FSC is again 217.5 into ASC is 628.31. So this I am going to write down in bracket divided by 0.36 into FCK is 20 into what is the B value? It is 300, right?
126.54.
126.54. This is the XU value. Okay. Now we have to compare this value with XU max. Before going to comparison, we can compare it with we have to compare it with XU max. Otherwise, we have to limit XU value to the maximum value, right? So how to find out now XU max? XU max is equal to, tell me the value, at least expression.
20 into
You have code with you, huh?
no,
Last time I have shown you that in the code the XU max values are given. Refer those values. XU max depends on grade of steel only.
okay.
So if you know grade of steel, you can easily find out XU max and those values are given.
0.53 into D.
Correct. 0.53 into D. Make use of code, huh? Have a habit of using code always. Don't need to mug up the values. So what is this value you are getting? 0.53 into D. Now D we have not calculated. Let me go back. Or we calculated it? No, we have not calculated. So I will write down here the D value, small d, as capital D minus DC because it is effective cover. So it is 380 minus 40. Tell me the value. 380 minus 40.
And
It
40
is
from both sides, no?
340. Sorry?
And 40 from both sides, no?
40 in both, yeah. Top, bottom cover, both. Normally, we provide the same cover at the top as well as at the bottom. So what is XU max?
180.2.
180.2 mm. So from here, we can find out XU is coming less than
Less than.
XU max. Okay. So whatever the XU value we have calculated, as it is, we can use for further calculations. Okay. Now the next step, we have to check whether our assumption, initial assumption is correct or not. For that, we have to find out FSC now, right? So find out FSC is equal to formula. Tell me the formula, FSC formula.
700 into 1 minus DC upon XU.
Correct. So put the values here. It is 700 into bracket 1 minus DC is 40 divided by XU is 126.54. Find out FSC value.
478.72.
Wait a minute. Tell me again.
478.73.
470.73.
8.73.
Okay. This is the value of FSC we are getting. We have to compare it with our initial assumed value. Our initial assumed value is 0.87 FY, okay? And its value is 217.5. So this value is coming greater than our assumption, that is 0.87 FY. It means assumption is correct. Assumption is correct. And anyways, when the FSC value exceeds 0.87 FY, we have to limit it to 0.87 FY only. So it is 0.87 FY, that is 217 point, what was the value?
0.5.
0.5 Newton per mm square. Okay, so our assumption is correct. Our XU value calculated is also correct. So let us put the value in MUR to find out the moment of resistance. So MUR expression I need now. Tell me the formula.
.36 FCK
Hmm?
D into XU.
Hmm?
In the next bracket, D minus 0.42 XU
Hmm?
plus FSC into ASC
Plus FSC into
into
ASC.
A. In brackets, D minus DC.
Correct. So put all the values here in this equation and tell me what MUR you are getting. So it is 0.36 into 20 into 300. This is XU, right? Into what is the value of XU we have got? 126 something, na?
126.54.
126.54.
Okay. Into bracket D is 340 minus 0.42 into 126 point, limit is over. 340 minus 0.42 into 126.54. I hope you can understand whatever I'm writing. Plus FSC value, can you tell me? It is 0.87 FY. So what is the value? 217
17.5.
point. Okay, 0.5 into ASC
628.31.
28.31. Okay, into bracket D is 340 minus DC is 40. So MUR is
119.4 into 10 raised to 6.
Correct. So it is 119.4 kilonewton meter. This is the MUR value. Okay, have you got it? We have solved only the first part of the problem, A part. We have calculated XU first by making the assumption. Then we compared the XU with XU max. Then we calculated FSC by using the expression. We checked its by comparing its value with 0.87 FY. We have checked whether our assumption is correct or not, and we found that our assumption is correct, and hence we calculated MUR by making use of the equation. We need to stop here today only. The remaining part we will see in the next lecture. Okay, the remaining part of the same problem, that is B part. Okay, and then we have to also solve the problems by considering HYSD steel bar. So this is the link for your attendance. I will put it in your chat box. Please give me the attendance through this link only.